Instrument Protective Function IPF classification, overview of IPF philosophy and instrumentation. Instrument Protective Functions IPFs are safety-related control functions implemented through instrumentation systems to mitigate risks arising from hazardous process deviations. These functions operate in tandem with mechanical protection layers to create a robust multi-layered safety strategy. IPFs are not ordinary control loops. They serve as barriers against process excursions that could result in equipment damage, environmental harm, or personnel injury. Each IPF must be independently verifiable, deterministic in behavior, and demonstrably effective across all credible operating scenarios, including startup, shutdown, maintenance bypass, and fault conditions. Hierarchy and functional integrity in safety instrumentation. The classification of an IPF reflects its functional criticality and performance expectation within the overall safety strategy. This includes specifying the initiating event, what triggers the IPF, the protection logic, how the function operates, the final element, what action it enforces, the response time and diagnostic coverage, how quickly and reliably it works. Each IPF must be aligned with its safety integrity level, SIL, derived from quantitative risk assessment. A higher SIL rating imposes more stringent requirements on failure probability, diagnostics, redundancy, and testing frequency. Hardware configuration and redundancy requirements. IPFs require hardware architectures that ensure fail-safe operation under fault conditions. Redundancy strategies such as 1-0-2, 1 out of 2, or 2-0-3, 2 out of 3 voting must be used where dictated by the CL or risk tolerance. The architecture must be resilient to single-point failures and allow online diagnostics and partial stroke testing, PST, for final elements, particularly valves. All components used in an IPF loop, sensors, logic solvers, and final elements, must be CL rated with third-party certification where feasible. Device integration must avoid common cause failures, e.g. shared signal paths or power supplies, and reflect environmental conditions and maintenance capabilities. Lifecycle documentation and validation. Each IPF must have a clearly documented life cycle, from initial hazard identification and SIL determination to design, installation, validation, and ongoing proof testing. The Safety Requirements Specification, SRS, defines the exact functional behavior, test intervals, and allowable degradation mechanisms. All maintenance and bypass actions must be logged and auditable, with compensatory measures defined to retain functional integrity during IPF outages. Separation and identification in field and control systems. To prevent inadvertent compromise, IPFs must be physically and functionally separated from the Basic Process Control System, BPCS, unless proven otherwise through independent verification. Field instruments serving both safety and control must be explicitly evaluated for potential common failure modes. In the plant, all IPF-related devices must carry distinct tagging, both in the loop diagrams and physical nameplates. Visual differentiation, such as red-on-black tags or distinct enclosure coloring, helps prevent unintentional modification or removal. Instrument cabinets and junction boxes associated with IPFs must be similarly marked and secured. Testability, diagnostics, and degraded mode strategy. IPFs must be fully testable within defined intervals, with diagnostic coverage designed to detect latent faults before demand. Systems should support automated diagnostics where feasible and provide degraded mode alerts to operators, including bypass status, test failure, and input loss. Upon detecting a fault, the system must default to a safe state and provide clear alarms. Where necessary, degraded mode strategies, e.g. override conditions, alarm escalation, must be defined and integrated into both the DCS and safety instrumented system. Integration with process hazards and alarm management. IPF design must be tightly integrated with process hazard analysis, e.g. HAZOP, LOPA, to ensure that the function responds to the correct hazard scenario. Where possible, IPFs should not overlap with high-level alarms or interlocks unless explicitly coordinated through the safety design strategy. Each IPF must be clearly mapped to its cause and effect logic, with time-stamped event logs available for troubleshooting and audit purposes. The alarm system must be configured to differentiate between IPF activation, process alarms, and equipment faults. Conclusion: IPF as a foundation of process safety. The effective implementation of IPFs requires a disciplined, auditable, and standards-driven approach throughout the plant lifecycle. These systems must be robust against environmental stress, maintenance lapses, and human error. By embedding clear classification, hardware redundancy, testability, and functional transparency, IPFs uphold the integrity of critical safety layers, ensuring plant protection even when primary systems fail. IPF classification criteria and risk-based design principles. Purpose of IPF classification. The classification of an instrument protective function, IPF, establishes the function's safety significance, performance requirements, and design expectations. This process ensures that protection systems achieve the required risk reduction while remaining cost-effective and operationally feasible. IPFs are typically classified based on the severity of the hazard they protect against, the likelihood of occurrence, and the effectiveness of other protection layers. This classification drives decisions related to hardware architecture, testing frequency, diagnostics, and failure tolerance. Risk reduction targets and SIL allocation. Each IPF must deliver a quantifiable level of risk reduction, which is translated into a safety integrity level, SIL. The SIL defines the allowable probability of failure on demand, PFDAVG, and shapes the design and maintenance strategy accordingly. For example, SIL-1 functions address lower consequence hazards or those with additional layers of protection. SIL-2 and SIL-3 functions protect against higher consequence events with fewer tolerances for failure. SIL-4, while theoretically defined, is rarely used in industrial process applications due to its extreme design and cost implications. The SIL assignment is typically derived from layers of protection analysis, LOPA, or similar semi-quantitative methods, with each IPF evaluated for independence, reliability, and effectiveness. Functional independence and avoidance of common cause failures. IPFs must operate independently of basic control and alarm systems to ensure integrity under failure or upset conditions. Independence extends to hardware separation, power supply, signal conditioning, logic solvers, and final elements. Shared components or pathways are only permitted if a detailed common cause failure analysis demonstrates acceptable risk. Where two IPFs share a common cause, e.g., shared valve or transmitter, risk assessments must evaluate whether the combined configuration still meets the required risk reduction target. If not, physical or functional separation must be enforced. Performance-based validation and proof testing. Each IPF must be designed for verifiable performance, with test coverage and diagnostic strategies aligned to its classification. This includes clear proof test procedures and intervals, monitoring of test success rates and failure modes, adjustment of test frequency based on field reliability data, automated partial stroke testing for valves where feasible. Test coverage must be high enough to detect dangerous undetected failures before the next demand, especially for SIL-2+ functions. The aim is to ensure that actual field performance aligns with predicted reliability models. Integration with operations and maintenance. IPF classification influences more than just design. It shapes how the function is maintained, bypassed, and overridden in day-to-day operations. Higher classified IPFs demand stricter bypass authorization and logging procedures, alarm prioritization and enunciation differentiation, operator training specific to IPF behavior and response, rapid repair or compensatory measures upon failure. All field maintenance, calibration, or modification activities affecting IPFs must be traceable, controlled, and reviewed to preserve functional integrity. Documentation and change management discipline. A complete and controlled documentation set must support each IPF, including functional description and SIL classification, verification and validation results, hardware and logic architecture, proof test procedures and intervals, change management records, bypass control protocols. Any change to an IPF, be it logic, hardware, calibration, or testing interval, must trigger a formal management of change (MOC) process. This ensures that any modification does not inadvertently reduce the IPF's effectiveness or invalidate its risk reduction assumptions. Conclusion: classification as the basis of functional confidence. A robust IPF classification process enables a transparent, risk-aligned instrumentation strategy. It ensures that safety functions are appropriately designed, verified, and maintained across the plant lifecycle. Classification transforms IPFs from mere control elements into formally accountable safety layers capable of withstanding the demands of real-world process hazards and regulatory expectations. IPF classification methodology, SIL assessment, establishing functional safety through SIL assessment. The safety integrity level assessment is the cornerstone of IPF classification, providing a structured, risk-based approach to determine the reliability requirements for each instrument protective function. The objective is not to over-design, but to assign the minimum required integrity that still ensures the risk is reduced to a tolerable level. SIL assessment translates risk tolerance criteria into measurable performance expectations, guiding design, verification, and maintenance decisions throughout the instrument's lifecycle. Each SIL corresponds to a specific range of allowable probability of failure on demand, PFDAVG, ensuring that risk reduction is quantifiable and traceable. Workflow for SIL determination. The methodology typically follows this sequence. Hazard identification. Process hazards are identified using structured techniques such as HAZOP or what-if analysis, generating a list of credible initiating events and potential consequences. Risk assessment. For each hazard, the severity and frequency are estimated. Factors include toxic release, fire explosion potential, equipment damage, and personnel safety implications. Layers of protection analysis, LOO. LOPA is used to quantify the residual risk after applying existing independent protection layers, e.g. relief valves, alarms with operator action, inherently safe design. If the residual risk remains above tolerable levels, an IPF is required. Target SIL selection. The required SIL is assigned based on the additional risk reduction needed. This can be done using a risk graph, risk matrix, or calibrated LOPA tables. The assigned SIL directly informs the PFDAVG and performance expectations of the IPF. Quantitative requirements by SIL level. SIL L1, PFDAVG, do 10 grids to 10 minutes. Typical risk reduction factor 10 to 100. SIL 2, PFDAVG, and 10 to 10 minutes squared. Typical risk reduction factor 100 to 1000. SIL 3, PF 10 min score to 10 p. Typical risk reduction factor 1000 to 10,000. My SIL 4, rarely used in process industries. PFDAVG grow 10 tennis facking to 10 max factor. Typical 10,000 to 100,000. Verification and documentation requirements as defined. The IPF must be designed and verified to meet or exceed the assigned performance level. This includes reliability modeling using tools like fault tree analysis, FTA, or failure modes and effects analysis, FME, selection of certified components with known failure rates, e.g. IEC 61508, 661511 compliant, evaluation of diagnostic coverage, test intervals, and safe failure fractions, documentation of assumptions, data sources, and calculation methods. The final output is a SIL verification report that confirms the IPF, as designed, achieves the required integrity level under defined conditions. Conclusion. SIL assessment as a design foundation. SIL assessment ensures that IPFs are engineered to perform their protective role with predictable reliability. By integrating hazard severity, protection layer performance, and failure probability into a cohesive framework, SIL assessment anchors functional safety in a measurable, repeatable, and justifiable methodology. It transforms safety from assumption-based planning into performance-based design. Consequences in IPF classification, understanding consequence severity, and SIL determination. In the context of IPF classification, consequence refers to the potential outcome of a hazardous event if the instrument protective function fails to operate as required. Accurately assessing the consequence is essential in determining the required safety integrity level, SIL, and designing a function that delivers the appropriate level of risk reduction. Consequence severity must be evaluated independently of likelihood. The assessment focuses on the maximum credible impact, assuming that the hazard occurs and no protection function intervenes. This creates a conservative, safety-first basis for determining functional requirements. Consequence categories. To support consistent SIL allocation, consequences are grouped into standardized categories based on the nature and severity of the potential impact. These typically include personnel safety, minor first aid injury or reversible exposure, moderate lost time injury or short-term hospitalization, major permanent injury or fatality to one individual, catastrophic multiple fatalities or large-scale personnel exposure. Environmental impact. Minor, localized recoverable spill within containment. Moderate, spill with off-site impact requiring cleanup. Major, significant release affecting public land, water, or requiring regulatory reporting. Catastrophic, long-term ecological damage or widespread contamination. Asset or equipment loss. Minor, local equipment damage, low cost to repair. Moderate, damage to multiple units, moderate repair time. Major, prolonged downtime, replacement of major plant items. Catastrophic, total unit loss, fire, or explosion. Reputation or regulatory exposure. Minor, internal issue with no public or regulatory awareness. Moderate, public concern or minor compliance breach. Major, legal action, significant regulatory violation. Catastrophic, license suspension, long-term brand or operational damage. Each category must be assessed using the worst case, credible outcome. The highest applicable consequence becomes the driving factor in determining SIL, regardless of how unlikely the initiating event might be. Integration with corporate risk matrices. Most organizations integrate these consequence categories into a corporate risk matrix. This matrix aligns consequence severity with frequency to define tolerability thresholds and the need for risk reduction. An IPF is then required if the unmitigated risk falls into an unacceptable region of the matrix. By tying SIL assessments to predefined consequence thresholds, the organization ensures uniform application of risk criteria across all processes and facilities. Conclusion: consequence drives protection demands. A clear, defensible evaluation of potential consequences ensures that IPFs are appropriately scaled to the risks they mitigate. Recognizing the full range of possible outcomes across safety, environmental, asset, and reputational domains supports transparent, accountable decisions in protective function design. By anchoring SIL to consequence severity, functional safety becomes aligned with real-world impact and organizational tolerance. Dangerous failure classification and IPF assessment. Understanding dangerous failures in the context of SIL. Dangerous failures are those that prevent an instrument protective function, IPF, from performing its safety role when demanded without generating a detectable fault or alarm in normal operation. Accurate classification of these failure types is essential for estimating the probability of failure on demand, PFDAVG, which in turn determines whether the IPF meets its assigned safety integrity level, SIL. All IPF components, sensors, logic solvers, and final elements are subject to failure modes. SIL verification requires quantifying how many of those modes are dangerous, and of those, how many are detectable through diagnostics or proof testing. Failure mode categories. Each component in the IPF loop is analyzed using standardized failure categories. Safe detected, SD, failures that do not pose a safety threat and are identified by diagnostics. Example, a transmitter drift that triggers an internal diagnostic alarm. Safe undetected, SU, failures that do not pose a safety threat but remain hidden until a scheduled test. Example, minor internal degradation with no immediate functional impact. Dangerous detected, DD, failures that could impair the safety function but are discovered through diagnostics. Example, relay coil open circuit detected by online monitoring. Dangerous undetected, DU, failures that prevent the IPF from acting on demand and remain hidden until tested or demanded. Example, valve stuck closed despite a correct signal to open, undetected until a trip occurs. Dangerous undetected DU failures are the most critical, as they directly influence the calculated PFDAVG and define the reliability of the IPF under demand conditions. Impact on SIL calculations. The fraction of total failures that are classified as DU determines the safe failure fraction, SFF. Higher SFF means the system can meet a given SIL with simpler hardware architecture. A low SFF requires greater redundancy or fault tolerance, e.g. 102 voting instead of 101. The goal is to minimize DU failure rates through use of diagnostics to reclassify DU as DD, frequent and effective proof testing, selection of field-proven or certified devices with documented failure rate data. Conclusion: dangerous failure classification as a design lever. Understanding and classifying dangerous failure modes allows engineers to optimize system design, proof test intervals, and diagnostics. By reducing undetected dangerous failures, designers can increase IPF reliability and compliance with SIL targets without resorting to unnecessarily complex or expensive architectures. This classification is not just theoretical, it directly affects plant safety, life cycle costs, and regulatory defensibility.